Okay, hi, I'm Aaron. I'm from Trace Machina, and I'll talk about Rules LL, which I'm the author of, which is a toolchain around LLVM. So the LLVM project has a Bazel overlay in the utils Bazel subdirectory, and you can use this to build Clang and various tools like LLVM AR and so on. And what RulesLL does is it takes a host toolchain from Nix, so it uses Nix as like a base layer. It then builds this Bazel overlay to get like Clang and all those tools, and packages this in a Bazel toolchain that you can then use to build actual targets, so your actual like end user code. In a way, this is just like another build system apart from the CMake build. Since we are building against Clang directly, like against the one that is in the LLVM repo, we can natively support things like C, C++, but also the more exotic targets like the offloading toolchains. Also, yeah, we have, of course, then access to the Clang tidy sources, so we can build Clang tidy from source in like a reproducible fashion, and also add like sanitizers, coverage, and so on. Basically everything that is in the LLVM project we can build, and we can build a toolchain around it with like a very nice development experience. The major difference between this approach and the CMake approach that I would say is the major difference is the kind of workflow that you have with this kind of system. So when we start basically here, where you're locally running a build, what you do is you invoke a Bazel test or a Bazel build, and this automatically fetches any pre-built artifacts that you have from previous runs of this toolchain. So when you start this from like the first time, when you build this the first time, you build everything from source, just like normal. But if you have, for instance, access to a remote cache, then you will just fetch the artifacts from your previous builds. And this gives you LLVM in 2 minutes on a laptop from like when you have a warm cache. And this is like upstream LLVM, or basically the commit that you specified that you wanted. When you then push your commit to a repository, usually you would have some CI runner. So for instance, a build bot, and this build bot then, or this CI runner then runs a test suite. And we in Bazel, you have a full like the entire build graph mapped out in like this tree structure, and it dispatches this then to different remote executors that you can scale up or down, and also you can choose like, I want a GPU for this specific action because maybe I have like a test that runs on a GPU or something. And all those executors also talk to this cache. So now you have this cache in your cloud, and then when you have another developer coming in, they will have access to this warm cache as well. And again, you basically, with this kind of system, you just build everything, maybe not always just once, but very, very few times compared to a standard workflow. This is how it looks like when you use Bazel instead of CMake. So you write your hello CPP. Note that we are using C++ modules here because we support it, of course, because it's part of libc++. So this is built natively into the toolchain. The build.bazel is basically your equivalent to cmake.txt or cmakelists.txt. You specify a name, the source files, and in this case, we set the compile flag to C++23, so we get this module support. And then you run bazel run hello. And how exactly it gets everything that you need for this build to work, it doesn't really matter. Like maybe you have access to a remote cache, maybe not. If you don't, then it'll just build everything locally. Note there is no like single-threaded configure step, no manual like creating a build directory or anything involved. This is an example of an offloading toolchain. So we built the entire hip/rockham stack from source. So this is like, I think, 8 or 9 repositories where I've I've ported the CMake build to Bazel for this to work. And when you add this compilation mode hip AMD GPU, and also like for NVPTX, we have a similar thing, then it'll build those sources. And yeah, this way you basically immediately get a build system that gives you the entire Rockham thing, and you don't need to build, you don't need to use the CMake build. When you want to, for instance, build some Clang tool, some front-end action that we'll hear about later, you can add this depends on LLVM flag, and then your build action has visibility, like has access to the LLVM headers, and it will link the LLVM libraries. Same thing for OpenMP. So this also just builds OpenMP from the LLVM project, and that's it. There's like no additional configuration. This is an example of Clang Tidy. So you can also build the Clang Tidy, like the compilation database, extract that from the build graph. And in this case, this will build a shell script that then invokes Clang Tidy. And you can, for instance, run this in like the distributed fashion, or you can run this across the entire build. And future developments are that actually most of the stuff that is now in the this cloud infrastructure, all the scheduling stuff is being developed in native link, which is from our company Trace Machina, and this is written in Rust. So if you want to to learn Rust, maybe take a look. Also for RulesLL specifically, we noticed that a big issue is the dynamic linking of glibc, and I would really like to swap this to muzzle. So because once you have this statically linked muzzle, we have everything in like a very easily distributable manner. Also, this paves the way towards WebAssembly, because the WebAssembly libc is actually just a variation of muzzle. And also from maybe if you were at the previous talks, there are also like Clang has offloading via OpenMP for targets like NVPTX and AMD GPU. So something like this, I keep playing with the thought of like maybe just adding that as well, because we already have a build system, so why not just extend it for these approaches? Yeah, thanks. Any questions? Do I have time? Or mm-hmm. 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 Yes, yes. So for instance, the Rockham stuff sometimes uses this for some custom things. So it does definitely require a bit more configuration. But what Bazel has is like a toolchain transition mechanism. So actually RulesLL bootstraps itself from this like host toolchain that we pull from Nix. And then it uses this bootstrap toolchain to build, for instance, libc++. Then it takes those targets, adds this together, and then you get a full-blown C++ toolchain. And the HIP toolchain is, again, like using the same mechanism where it transitions the toolchain into this more extended variation of the toolchain. So this is what you can use for these kinds of things. And when you have something, for instance, like the CL or bitcode stuff, you can, there is in my opinion, much cleaner way to specify these things in Starlark, which is basically Python. So you have kind of like Python scripts that that just map out the different arguments and have like inputs, outputs, and so on. So these rules, like the LL binary, you can write your own, and you can do whatever you want with this. Mhm. Mhm. So Bazel is just the thing that that gives you the API to build toolchains. And the default toolchain is actually rules CC. And RulesLL is a pure Starlark re-implementation of rules CC, because rules CC is built into Bazel, and so it's very hard to change stuff. And also, for instance, it doesn't differentiate between the C and the C++ compiler, which can be a big issue when you want more like complicated toolchains. And so RulesLL implements this toolchain logic on top. There are also, for instance, rules Java, rules Rust, and so on. So when you have larger projects that use multiple languages, this is like way nicer to just make all of those interoperate with each other. For instance, like TensorFlow, PyTorch, the entire like a lot of the AI stuff is using Bazel because of this, because it's easier to make languages interoperate languages in a build. So this is something that is definitely possible, but I think not currently supported in RulesLL. There are platforms where you can specify, hey, I want my target platform to be this and that. And so like cross compilation is definitely a more like complex topic, but this is also possible. Also, you already get like a like fairly large amount of freedom regarding architectures, because in this case, since we are based on NICs, like your distribution doesn't matter. So this is already abstracted away. And then, yeah, so but for like a different CPU architecture, this definitely will take some more work.